Here's a video solution to your week 14 handout. Okay, problem number 1: a uniform disc with mass 2.5 kilogram and radius 20 centimeters mounted on a fixed horizontal axle. A block with mass 1.2 kilogram hangs, sorry, that should be hangs from a massless cord that is wrapped around the rim of the disc. Find the acceleration of the falling block, the angular acceleration of the disc, and the tension in the cord. The cord does not slip, and there's no friction at the axle. Okay, so cord does not slip, so you have to include in a rotational inertia in this case, and so we are talking about the friction in an axle itself. Okay, what's given? Okay, radius 0.2 meters, inertia of a disc 1/2 mr, radius of the disc square, mass of a disc 2.5 kilogram, mass of a block 1.2 kilogram, acceleration alpha is acceleration equals to alpha times r, the net force, these are the formulas that I'm writing, torque equals to I times alpha. All right, so now if you're looking in a string, so tension on this edge here, okay, and this edge, tension is acting in both direction, right? Sorry, the Newton's third law, right? The magnitude of tension. So if you look at the disc itself, tension is acting down. This is what's creating the torque, right? So the net torque on the disc is I times alpha, okay, which is in a clockwise direction. It's rotating clockwise, so that's negative. So torque is created by R times T, which is perpendicular, so that is R times, and sine of 90 is 1. So R times T, I times alpha, so net torque is in a negative direction. So tension is I alpha over R. So inertia is 1/2 mr squared. Alpha is A over R, so it's divided by R. So that gives you R, and R cancels out, right? And then this R and this R cancels out. So tension equals to 1/2 MA. That's the magnitude of tension. Okay, so that's the magnitude of tension. To find the tension, we need to know the linear acceleration. So to find the linear acceleration, we're using this block here. Okay, so summation of force equals to MA, right? So in this case, force down is mg minus T equals to MA. Okay, so we need to find acceleration first. So we know the magnitude of tension, so mg minus 1/2 MA equals to MA. So put acceleration on the same side, mg equals to MA plus m over 2a. Acceleration, okay. G, so 2mg, 2m plus m, okay. So you will get 4.8 meters per second squared. Now you take tension, okay. Now you can find the magnitude of tension. Acceleration 4.8, sorry. Let me erase that. I'll just put that acceleration A. You plug in the values, you get tension to be 6 newtons. All right, the next question here, okay. So two 6.2 kilogram blocks are connected by a massless string is still massless, over a pulley of radius. Why are there so many errors here. See, and rotational inertia 7.4 times 10 to the power negative 4 kilogram meter squared. The string does not slip on the pulley. It is known whether there is friction between the table and the sliding blocks. The pulley's axis is frictionless. When the system is released from rest, the pulley turns through 0.130 radians in 91 milliseconds, and the acceleration of the block is constant. What is the magnitude of pulley's angular acceleration? Magnitude of either block's acceleration, string, tension 1 and tension 2. All right, so let's see what's given. Radius 0.024 meters. Okay, that's for the pulley. Inertia of the pulley, that is 7.4 times 10 to the power negative 4 kilograms meter squared. Theta, okay, theta is 0.130 radians. Time it took is 91 milliseconds, so that is 0.091 seconds. Okay, so let's draw a free body diagram. Force normal, force gravity, tension is in that. So if you're just looking at the block, tension would be in that direction. If you are looking for the pulley itself, T2, T1. Okay, so both will be accelerating in the same direction. So A1 equals to A, that's the magnitude. M1G, T1. Okay, so for this block, this is M1G minus T1 M1A. And for this block here, that will be T2 minus friction. Sorry, there's friction static. Okay. So we are talking about acceleration. So we are just worried about friction here. Let's not generalize friction. So friction kinetic in this case. M2A. All right. So now let's find alpha. Okay. So in this case, this is the radius. So torque net is I times alpha. Pulley is the one that's rotating. So T1R minus T2R equals to I times alpha. A equals to alpha R. Okay, we need to find A first. Okay. Or the alpha first. Okay, to find the magnitude of A. Okay. So let's start with kinematics, rotational kinematics. Theta equals to theta initial plus omega t plus 1/2 alpha t squared. Okay, theta initial. So if we started from rest, okay, theta initial is 0. So 0 started from rest. So this is 0. So we can find alpha. We know theta, that is 0.130 radians. 1/2 alpha t squared, that is, oh sorry, I never want to do it this way. Okay, so 2 theta over t squared equals to alpha. Okay, if you plug in the values, you get 31.4 radians per second squared. Okay, from that we can find A, which is 0, sorry, A would be alpha, that is 31.4 times radius, that is 0.024 meters, that is 0.754 meters per second squared. Okay. From that you can find T1, So T1 equals to M1G minus M1A. So M1G minus A equals to 56.1 newtons. Okay. So now we need to find tension 2. Okay. So we can, instead of using this part here, okay, and using friction, we can directly plug this into this equation here to find tension 2. So T1R minus T2R equals to I times alpha. So T1 minus T2 is I alpha over R. So T1 equals to, sorry, T2 equals to T1 minus I alpha R, which is 55.1 newtons. As you can see, T1 and T2, magnitude of T1 and T2 are not the same, okay? Because we have included the inertia for the pulley. So when we worked with similar problem, and when we worked on chapter 5, 4 and 5, we did not include inertia of the pulley, okay? We ignored it. So in that case, tension in the string was the same. So now we know the rotational inertia. We cannot ignore that anymore. So as soon as I mentioned rotational inertia, make sure you involve inertia rotational part in your solution. Okay. All right, that's all. So I'll be seeing you for lecture 21 on Zoom after Thanksgiving.